Right, we're going to do some work here today about curve sketching and the old derivative. So we're going to start by looking at question 8, when I get this eventually working, and then we're going to look at question 5 as well, and these two different ones. So they're getting you looking at different things, but mainly you just need to be finding all the important features and then eventually sketching the graph. So the first one for 8. So we've got f of x, which is equal to x cubed minus 3x, and we want to show the first derivative and the second derivative. Let's show the first derivative first. It's going to be, bring the 3 out the front, subtract 1 from the power, minus 3. Factorize out of 3, out of both terms. Now what you'll notice, this x squared minus 1, that is a difference of 2 squares, which becomes x plus 1, x minus 1, as is provided right here. We can then take a look at the second derivative. Now, there isn't really any need to use it in this form when you're finding the second derivative. This form here that we found initially will be the easiest thing to derive. So 2 going to come out the front, 2 times 3 is 6, and the constant term just vanishes, becomes 0. Shows that it's 6x as required. Now we're going to find the stationary points, and we find the stationary points by looking at when the first derivative is equal to 0. So when we have 3x squared minus 3 is equal to 0. In this situation, we could have the form that we were asked to find it in, or we can simply solve what we've got in front of us. Let's add 3 to both sides. 3x squared is equal to 3. Divide both sides by 3. We're going to solve this equation. And then we're going to square root both sides. Now it's plus or minus the square root of 1. So it's plus or minus 1 because negative 1 squared is still 1. We still end up with the same answer. It's going to be very important. So that are the x coordinates of my stationary points. In order to find the y coordinate, we're going to substitute x is equal to 1 into my original equation here. And we're going to put x is minus 1 in there as well. So when I put x is equal to 1 in there, I'm going to get minus 2. And when I put x is negative 1 in there, I'm going to get positive 2. Which ended up working out quite nicely, which is good. Doesn't often work that way. Now what we're going to look at is determine their nature. So using the second derivative to determine their nature means asking, is it a maximum or a minimum? And by substituting into the second derivative, if I put 1 in the second derivative, I'm going to get 6 times 1, which is 6, which is greater than 0. Which is a minimum. If the second derivative, when we substitute in our x value, is greater than 0, it's a minimum. And if it's less than 0, like we see here, when we substitute in our other x coordinate, it's a maximum. Remember that a minimum, concave up, U-shape, maximum, concave down, N-shape. Find the coordinates of the point of inflection. So, a point of inflection is when my second derivative is equal to 0. So my second derivative is equal to 0. We've got 6x equals 0, which is at when x is equal to 0. We can find the y coordinate by substituting it back again. Original equation up the top there. We get 0, 0. That is a possible point of inflection. To determine if it is a point of inflection or not, we will need to test on either side, the x values on either side, to see if it changes. Now, we've kind of in a way done this already. We have negative 1, 0, 1. We know that sign is 0. Now we know that 1 is greater than 0, it's positive, and negative is less than 0, negative. And we did this earlier because we happen to have 1 and negative 1. The sign changes, therefore, it is a point of inflection. I'm just going to put POY at 0, 0. Now that we have all of this information here, it's going to allow us to graph it. If we rule up a beautiful artsy graph right here, we got 1, negative 1, we got 1, 2, negative 1, negative 2. We've got my point of inflection. I'll do it in a different color. We've got my point of inflection here in red. We have at 1, negative 2, we have our minimum turning point, 1, negative 2. That's going to be my minimum. I'll draw a little minimum there to know. And negative 1, 2 is going to be my maximum. And the concavity changes at that point of inflection. So we have a graph that looks something like this little bit of garbage that I've drawn over here. Not super accurate, but it's going to get the job done. And what we can do is we're just going to jump straight into the second one. Very, very similar ideas of what we're going to be looking at. So we're going to find the stationary points and we're going to work from there. I'm just going to delete this at the bottom so that I've got plenty more space to write with. And then we're going to jump in and take a look at question 5. I'm going to do this in red. I say red. Question 5, we got A. Show that this here is an odd function. Now, to show whether a function is either or odd, we're going to put in f of negative x into my function. 27 negative x minus negative x cubed. Now, what we would do here in this situation, by expanding it, plus x cubed, negative x cubed is still going to be negative x. Negative, negative makes a positive. If I can factorize a negative out of my function and get the same function that what I started with, it is odd by definition. If I can factorize out a negative and get the same function, it's odd. If I put in a negative and I just end up with the same function, then it's even. So this being odd is going to be important. Now we can look at the first and second derivative. So we've got my function here. Differentiate it to find the first derivative. Whoa. It's 27 minus 3x squared. Now, it wants us in this form here, like in the question. So to do that, we're going to need to take out the highest common factor, which is 3. Now, this right here is, again, what we've got there is a difference of 2 squares, just like in question 8 above in the earlier question. So we could factorize that as a difference of 2 squares again if we like, but we don't need to. And it's actually not going to benefit us to factorize this any further. It's actually going to make things a little bit more difficult. So we can find the second derivative as well by differentiating what we had above, and we end up with negative 6x. 2 comes out the front, 2 times 3 is 6, take 1 away from the power. Let's find the coordinates of the stationary point. I'm going to do C down here. I believe I can scroll down a little bit. Maybe not as much as I thought. Stationary, when the first derivative is equal to 0. We have the first derivative here. We have 27 minus 3x squared is equal to 0. Let's solve this. We want to isolate x. Add 3x squared to both sides. We have 27 equals 3x squared. We can't square root yet. We want that to be the last thing we do. We're doing BIDMAS essentially in reverse order. So we're going to get rid of this 3 first by dividing. Remove the multiply and divide before you remove the powers. So we have 9 equals x squared. And again, x is going to be equal to plus or minus the square root of 9. The opposite of squaring is the square root, which is plus or minus 3. Now, we can find the y coordinates by, again, taking this and substituting it back into the original equation. So when it's 3, I'm going to quickly type this into my calculator right now. We have 54, good Lord. And when we have negative 3, when I substitute that into the equation, I end up with negative 54. Excellent, 2 lovely numbers. Determine their nature. So we can determine their nature, once again, using the second derivative. Because I already have the second derivative here, it's going to be a little bit easier. It's also going to be faster, and as you can see, I'm kind of running out of room as well. So let's put in 3 into the second derivative. Is negative 18. It's less than 0, so it's a maximum. And if I put in negative 3, I'm going to get positive 18, greater than 0, so it's a minimum. We've got the 2 values of my stationary points. We've completed A, B, and then C. Now what we need to do is to show that is a point of inflection. To find a point of inflection, we solve when the second derivative is equal to 0. So that's negative 6x is equal to 0, x is equal to 0. Substitute the x value into my original equation to get the y value, which will be 0. 27 times 0, 0, minus 0 cubed, 0, 0. And then again, we do the testing the signs. we have x. And once again, we can use the values we've already done. We've already put in -3 and 3. We've seen that the sign is different. When I put in 3, I get a negative. When I put in -3, I get a positive. The sign changes, therefore it is a point of inflection. All of this different information is going to allow you to graph it. You can find the gradient of the point of inflection by putting 0 into the first derivative, and you're going to get 27. That's a pretty substantial gradient, and you're going to find this a lot of the time. It will make your graph a little bit more accurate, but getting this isn't super reliable for your drawing unless your drawing is going to be like the greatest, most accurate drawing of all time. So if we go back to what we're going to be looking at, we now have all of this different information. We know there's a point of inflection at 0, 0. We know that 354 is a maximum. So we have 354, which will be up here, maximum. We know -3, -54 is a minimum. So we can connect all these together and we end up with a curve that's going to look just like that. By having the gradient of 27, your graph will be a lot more nicer than mine. And we get 27 again by substituting x as 0 into the first derivative. But this is my graph here, which is what we want to see. It's got all the important features. You can find the x-intercepts by letting y be equal to 0. But the main important features are the turning points and the point of inflection right there. And that is curve sketching using the first and second derivative.